Okay, hello there. So this is going to be the first meeting regarding the lecture material for the course. So I hope you're doing well. I will have other meetings. You may notice that there's already, I made an announcement on Blackboard that there's already all the videos for chapter 3 are there. But in the spirit of practice, I'm going to continue to do more videos of these problem solving sessions. And if you ever want to join in, you're free to join in and ask specific questions. We can work on specific questions that you might have, difficulties that you're having. That can be very helpful for people to see the challenges that other people are having with the problem. So I hope you're doing well. Hope you're being safe. I hope that you enjoy this course. So what I'm going to do is I'm going to start in section 3.2, which is percent composition. And I'm going to look at a few problems here over the next 45, 50 minutes or so, and give you some insight into those problems on Alex. So let me share the screen here. Okay, so there you can kind of see what we have here. So for chapter 3, there's 22 topics. That's the most topics of any chapter in the course. There's a lot, but many of the problems are pretty simple. Percent composition is in section 3.2. That's our first type of problem. There's only one problem in that section. And then we're going to move on to some chemical equations and stoichiometric coefficients and so forth and so on. Generally speaking, the first two sections, 3.2 and 3.3, are pretty easy for people. But then when we get to mole and molar mass, sometimes that can be a little bit challenging. So the material in the chapter gets more and more sophisticated. Okay, so let me bring up the first type of problem. Here we go. Finding the mass percent from chemical formulae. Okay, so I want to point out that when you're doing calculations involving mass, I do recommend that you use the Alex periodic table, because the periodic table that Alex has is the calculations are done with that table in mind. So the number of significant digits in your answer are going to be based on the Alex periodic table. So if you use a different periodic table, and then to be honest with you, because when I do instructor access, I don't have access to the periodic table on Alex. I'm going to use this little chart that I have here. These numbers are slightly different than the ones on Alex. So if I were to actually use these numbers on Alex, I'd probably get the wrong answer. It'd be very, very close, but the software is a stickler for that issue. Okay, so let's take a look at this first type of problem, and I'll pay attention a little bit to significant digits as well, because you may need some brushing up on that, rounding and all of those issues. So this is the chemical formula of methyl acetate. So here's methyl acetate there. It's got carbon atoms and hydrogen atoms and oxygen atoms in it. Calculate the mass percent of carbon in methyl acetate. Round your answer to the nearest percentage. Okay, so what I'm going to do is, let me stop share there. I'll bring this up here. And let me write the formula down. It's CH3 2 CO2, methyl acetate. Okay. Now, one of the things I'm going to do is I'm going to show you, this is not necessary for the problem, but I'm going to show you the arrangement of the atoms. Okay. So, oops, sorry, I forgot. I made a little mistake there. Let me fix that mistake. forgot that hydrogen, I mean that oxygen. There we go. Okay, now you can sort of see that. So this is our methyl acetate. And notice it's got a CH3 here. So I'll circle that CH3. Another CH3. So there's your CH3 too, right? That means that there's two CH3s. And then you got a CO2. Okay. So sometimes formulas are written in different ways. There would be different ways we could write this formula, but what's being shown is essentially what's considered a condensed form. This is called a condensed form over here. And it doesn't really matter what the structure is for this problem, but I just wanted to show it to you just so you can see it. So in any case, in this problem, we are asked to determine the percent carbon. So we want to know the percent carbon. I have to go back and look at that. Okay, so let's count up the number of atoms of each element. So let's do carbon first. So there's CH3, that's one carbon. When there's no number next to the element symbol, that means it's a 1. But this is in parentheses here. That's the key. That parentheses means that everything that's inside the parentheses is going to be doubled. So there's 2 carbons right there. But then there's another carbon here. So 2 plus 1 is 3. So it's really C3. Okay. How many hydrogens? Well, you got 3 here as a subscript. That means 3 hydrogens. But again, you have this other subscript outside the parentheses. 3 times 2 is 6. So it looks like it's 6. And then the only oxygens are outside the parentheses. There's 2 of them, right? That subscript means there's 2. So there is a formula that will allow you to get the percent carbon a little more easily. So here's the way we calculate this. Percent by mass of carbon. So I'm just going to write percent C for carbon. Okay. What you do is you count up the number of atoms of the element that you're interested in. So we're interested in carbon. So 3 times, I'm going to put this in parentheses. You go to your periodic table and you look up carbon. Carbon has a mass of 12.011. Now the units are typically in AMU, atomic mass units, okay? So the periodic table, you look at that number that's underneath the symbol, that's called the atomic mass. We talk more about that in Chem 100, the previous course in the sequence. What the atomic mass is, it's essentially the average mass of a carbon atom, okay? And the units are atomic mass units or AMU. Then we divide that by essentially the total mass. Now, how do we calculate the total mass? Well, same way. You just say how much is all the carbons, all the hydrogens, and all the oxygens weigh. So 3 times 12.011 AMU plus 6 times 1.00794. I'm going to need to expand this quite a bit. And then 2 oxygens, 2 times 15.9994. Okay, now there's one issue here that I need to have room here. It's times 100, where we're converting it to a percent. So we multiply by 100. Okay, I'm sorry you can't really see that. Times 100. Okay, to convert it to a percent, all you're doing. So what are we doing here? We're saying, look, we want to know what percentage of the total mass is due to carbon. Well, the percentage due to carbon would be how much the carbon weighs divided by the total. So it's really the mass of the carbon over the total mass times 100, just to convert it into a percent. Okay, that's all you're really doing. So you just have to figure out how many carbons you have, how many hydrogens, how many oxygens. Be careful in the denominator. I would recommend when you do these calculations, at least at the beginning, is to do the numerator calculation first. So do your 3 times 12.01. Okay, I just did that calculation. Then I'm going to do the denominator calculation. Now for that one, I'll use my calculator. You've got 3 times 12.011 plus 6 times 1.00794. This actually, these numbers I'm putting in here would probably give you the same answer as the ALEKS software would. And down here at the denominator, it becomes 74.079. Now look, this one's going out 4 digits past the decimal point. This one's going out 5 digits past the decimal point. And this one's going out 3 digits past the decimal point. So I'm going to write a little line above the 9 because that's the 3rd digit past the decimal point. So in practice, what you do is just, go ahead and write down the number your calculator has. 74.07944 is what my calculator has. And that looks about right. Yeah. So I'm going to write that whole number down, but then I'm going to put a little line to indicate that when you're adding numbers together, you'd locate the decimal point in all of the numbers you're adding or subtracting, count out how many digits past the decimal point each one goes, and pick the one that goes the fewest past the decimal point. So that first digit, that first measurement here, carbon, only goes 3 digits past the decimal point. So our answer in the denominator is going to end at the 3rd digit past the decimal point when we consider significant figures. Okay, so now I'm just going to go ahead and run this through the calculator. So divide that by, okay, and then multiply by 100. And let's try this again. I'm sorry. 36.033 divided by 74.07944 times 100. And you get about 48%, but we're going to be more precise about that. 48.6410. I could put one more even if I want to. That's the percentage carbon. In other words, almost 49% of the total mass of this compound, the methyl acetate, is due to carbon. But we still have to do another step with significant digits, and that we did the denominator. We considered the figs there, significant digits. And that's why I drew that line above the 9 to indicate that we can't go beyond the 3rd digit for that number in terms of our final answer. So now what I'm going to do is I'm going to say, how many digits do I have here? 5 digits. How many digits do I have up to the 9? 5. They both have 5. So that means our answer is going to have 5 digits. Okay. So we round it. 1, 2, 3, 4, 5. So we're going to end right there. The 0 is less than 5, so we can just truncate it. We can truncate every number that comes after it. So we have 48.641, and that would be percent carbon. Okay, so notice in this problem, we have to do 2 separate considerations of significant digits because there's 2 separate operations occurring. The first one is addition subtraction. So with addition subtraction, you count the number of significant digits past the decimal point. Let me reorder those. So, T, W, X, Y, Z. There's 5 significant digits past the decimal point. If you're adding or subtracting another one, what you do is you count the number of significant digits for each one. This one goes 3 digits past. This one goes 5 digits past. Okay, so when you add them or subtract, it's the same principle for subtraction. You're just going to go 3 digits past the decimal point. You round it to 3 because this one only goes 3. Okay. But notice, even though I put that line there, I still use the numbers that came after it because we don't want to do intermediate roundings. You don't want to round more than once in a problem. It leads to what we call rounding error. So don't do the actual rounding till the end. You note where the last significant digit is in your calculation. Second step, now we're doing multiplication division. That has a different consideration. With that one, this is simpler in a way. All you do is you count how many digits there are. So let's say the one in the numerator has 5, and the one in the denominator only has 2. You would do the calculation, put all the numbers in as you have them, put them into the calculator, and then round them to 2 digits, the fewer number of digits. Okay, so I'm just using letters here instead of numbers, but you know, I can do RS, right? So this one only had 2 digits, this one had 5, so our answer is just going to have 2, the fewer number. Okay, so there you go. There's your atomic mass. The atomic masses come from the periodic table. Those have already been tabulated for you. I would recommend, you know, taking the ALEKS periodic table and printing out a copy of it if you can, and just have it next to you, or have a different window, I guess. If you can have a different window open, that would be helpful too. But I'm not sure whether ALEKS even allows you to have the periodic table on a different window. In any case, you want to have a copy of it available so you can do these problems. Okay. All right. Let's stop share here. And then I'm going to come up. Oh, let's take a look at their explanation. Okay. I just want to show you. See, they give a little explanation. So let me share the screen here. Okay, see that one? So all I did was I clicked on explanation. So that's going to give me an explanation. You know, they give slightly different descriptions of things than I do, but that's fine. It's really, we're looking at the same thing. And then, so they're using, here's a difference. They're already doing grams per mole. Most textbooks will do these in atomic mass units, AMU. Grams per mole comes up in section 3.4, but ALEKS, for whatever reason, they've already integrated it into grams per mole. The units of grams per mole versus AMU, it's an issue. It's a serious issue, but you will get the same percent answer whichever units you use. Okay, so you'll see grams per mole and moles there. We'll talk about that. But then they added the numbers together, got your 74.07464. Okay, so you've got that. They did what the mass fraction for all 3. They did it for all 3 elements, carbon, hydrogen, oxygen, but you didn't need to do that. You just needed to do carbon because the question asked about carbon. Okay, there's your total mass, which is, you know, we'll see that's called the molar mass. And then they did the percentage breakdowns. Okay, so actually looking at it, in this question, calculate it, round it to the nearest percentage. So that's one of the things you have to be very careful about. I did a full-blown significant digit analysis for this problem, and I didn't read a really minor detail. It seemed like a minor detail. It says round it to the nearest percentage, okay? So that's pretty simple then. All you're really doing is you're taking your percentages and, you know, rounding it to the nearest percent. Okay, so I'm sorry that I didn't notice that, but you're just going to round it to the nearest percent for that one. So be careful. Read the question. I have to get into practice myself for reading very carefully. Typically we would do it the way I said, but for them they just said round it to the nearest percent. Okay, so there you go. So there's that problem. I want to show you another one on balancing equations. Sometimes balancing equations can be pretty simple for people, but sometimes it can be pretty challenging. So what I'm going to do is I'm going to go straight to the most advanced of the balancing equations problems here. There's 4 different balancing equation problems, and this is the 4th one, which is the most challenging. So I want to focus on this one. If you can do this one, you can do the easier ones, okay, the other 3. So this says writing a chemical equation from the description of a reaction. And it says that phosphorus trichloride gas is obtained by the reaction of chlorine gas and solid phosphorus. Write the balanced chemical equation for this reaction. So a reaction is a process you observe occurring. So for example, digestion is a bunch of reactions. Those are processes. It is sometimes the case that we can write an equation, which is like a mathematical equation. We call it a chemical equation for some sort of chemical process. So an iron, a nail is rusting. I'm sorry, like a seashell is forming from calcium and carbon dioxide in the water, right? That's a chemical reaction. The acid digestion of a protein is a chemical reaction. We can write equations to represent them. So the idea is you have some sort of thing occurring in nature, a reaction. Then you write a symbolic equation to represent that process you're observing, right? So, let's take a look at this one. This one has issues in it that I want to bring up, and we'll take a look at it. So phosphorus trichloride. So let me stop share there. So it says that phosphorus trichloride gas is obtained by the reaction of chlorine gas and solid phosphorus. Okay, write the balanced chemical equation for this reaction. Okay. All right. So let me go over this one. Like I said, it has a lot in it. The terminology is quite variable, and you're just going to have to get used to that. Is obtained. So is obtained means the same thing as produces or forms. You'll see different terms used for that, okay? The idea of a chemical equation is that you have these substances that are called reactants, and they're added together. They're separate substances that are added together. Now, since there's more than one in this example, I'm going to call them 1 and 2. So 2 different reactants. They will undergo some sort of process, which we call a reaction, that will form 1 or more products. So I'm going to show it as 2 products, although it could be 1, it could be 3. And since, again, there's more than 1, I'll write 1 and 2. Okay, so it doesn't have to be 2 reactants, 2 products. It could be 1 reactant, 3 products. It could be 3 reactants, 1 product, 2 and 2, 4 and 1, 3 and 5. It just depends on the situation. But in principle, the idea is that we're going to use this idea of an equation. This is called a chemical equation. And we're going to use it to represent a chemical reaction. Okay, so the reaction is what happens in nature. The chemical equation is our representation of it, kind of like we do in algebra. Okay. So let's start with this. It says that phosphorus trichloride gas. So it's telling us some information. It's telling us that it has phosphorus. It's telling us that it has chlorine. Chloride is the same essentially as chlorine. There's trichloride, so that's a 3. Okay. It tells us it's a gas, so we put in parentheses a G. Okay, so phosphorus trichloride gas is obtained by the reaction of chlorine gas. But it turns out there are 7 elements in the periodic table that exist as what we call diatomic elements. So there's a 2 subscript. Okay. So it's formed from the reaction of chlorine gas, again, notice the G, and solid phosphorus. So here's phosphorus, and it's a solid. Okay. So now the arrow generally points toward the product. That's how we do it. The arrow should be pointing toward the product. So the product is the one formed. So that would be PCl3. And then the reaction of, meaning those are the reactants. So these 2 are the reactants. Okay. So the arrow should point towards the product. So I'm going to write it this way. Cl2 gas plus P solid forms or is producing phosphorus trichloride as a gas. Okay, so notice even though phosphorus trichloride was the first thing it told us about, that doesn't mean it's the reactant. We have to infer from the language which is the reactant, which one is the product. Okay. Now we can get to the balancing. The balancing is relatively simple. The balancing means that we have to have the same number of atoms of each element on both sides. So let's start with the phosphorus. Why am I starting with phosphorus? It's the easiest one. There's one phosphorus on both sides, right? So we would say that it's balanced. If you have one on the left side and one on the right side, that's balanced. The chlorines, however, are not balanced. See how there's a 3 on the right side? And there's only a 2 on the left side? We can't change those numbers. We can't change those subscripts. But what we can do is we can change what are called coefficients. So if I write this, 3O2, this refers to what we call a subscript. This is called a coefficient. The coefficient tells you how many of these substances you have. The subscript tells you how many atoms are in one of those substances. Okay? So we have a math issue now. Essentially, what we can do is we can change the coefficients. So what I'm going to do is I'm going to write an A here and a B here. We're going to change A and B so that when you multiply 2 times A, it's equal to 3 times B, right? The subscript times the coefficient should be the same on both sides. So 2A has got to equal 3B, okay? That's essentially the idea. Now, the simplest thing you could, or one of the simplest things you could do, is you could just start plugging in numbers to see which combinations work. So for example, if I put in a 1 for A, 3 times 1, I'm sorry, 2 times 1. And if I put in a 1 for B, I'd have 3 times 1. That doesn't work, right? 2 is not equal to 3. So I could just start adjusting those numbers ever so slightly. I could make A2, and that would give me 2 times 2 is 4. And I could use 2 for B. 3 times 2 is 6. Well, that doesn't work either. So let's try the next number. Let's try A is equal to 3. 2 times 3 is 6. Okay, so 2 times 3, that's equal to 6. Now I could come over here on the right side and I could say 3 times what is equal to 6? That's my question. What would B have to be such that when you multiply it by 3, you get 6? And it's clearly 2, right? 3 times 2 is 6. So that means B should be equal to 2 and A should be equal to 3. Okay, so I'll put those in. Did that work? Yeah, we've got 6 chlorines on both sides. The coefficient times the subscript is the number of atoms of that element. Now, one of the things that happened, though, is that we put a 2 in front of the PCl3, so now we have 2 phosphoruses. So even though we originally had 1 phosphorus, now we have 2. So I'm just going to put a 2 over here. And now that one is done. Okay, so relatively simple. 3Cl2 gas plus 2P solid gives you 2PCl3 gas. We now have a balanced equation. Okay. Now, how did I know that the chlorine, when it said chlorine gas, why didn't I just write Cl? Why did I write Cl2? It turns out there are 7 diatomic elements. So what I'm going to do is I'm going to write down here the 7 diatomic elements. The first one is hydrogen. So when a problem says that hydrogen reacts or hydrogen is produced, you want to write it as H2. The same goes for nitrogen. We would write that as N2. Oxygen, we would write that as O2. Fluorine, F2. Chlorine, Cl2. Bromine, Br2. And iodine, which is I2. Okay, so that's 7, right? And just to kind of help you sort of think about it, hydrogen is in column 1A. So it's this one here. So you got hydrogen, lithium, sodium, potassium, rubidium, and cesium. So that's column 1A or family 1A of the periodic table. Then you have column 2A. Now 2A is empty in the first row for reasons we'll get into later in the course. And none of these elements are diatomic. So far it's only hydrogen. Then you have the transition metals, which are, group 3 through 10. And those ones, we're not going to worry about them at all. They start over here with scandium and so forth and so on. But now we're going to come back over here to, I'm running out of room. So let me get rid of the transition metals and just point out the transition metals, we're going to ignore them. Then all the way over on the right side of the periodic table, so, we'll do it this way. There's a big empty space there. 3A would be boron and aluminum and gallium and indium. Why don't I just go ahead and write them all out? Gallium, indium, and thallium. Okay, don't have to worry about those for this issue. 4A is carbon, silicon, germanium, tin, and lead. Okay, now it's when you get to 5A that it becomes an issue again. It's nitrogen. Okay, so I'm going to circle this one. Okay, not phosphorus. You don't have to worry about phosphorus. Remember with phosphorus, I didn't write P2. I just wrote P. Underneath phosphorus is arsenic and then antimony. And then I think it's polonium. Yeah, no, bismuth. I'm sorry, bismuth. Okay, so far it's just 2. Group 6A is oxygen. So that's the third one. And then this is sulfur, selenium, tellurium. And there's your polonium. I was thinking polonium instead of bismuth for group 5A. And then group 7A. So fluorine, chlorine, bromine, and iodine. And then underneath iodine is astatine. I don't know, it's kind of interesting, but it's these four here. So there's your 7 diatomic elements. So it's the first 4 in group 7A. These are called the halogens, by the way. Group 7A is called halogens. Halogens, like a halogen lamp. You've heard of that. The halogen lamps have halogens in them. Fluorine, chlorine, bromine, and iodine. So those are these 4 here. Okay, so in fact, you can write a little box here. Those are diatomic. It's also oxygen and nitrogen. So notice these 2 here. So 6 of the 7 are just on that little corner there, group 5A, 6A, and 7A. And then you got the hydrogen over here, this one right here. Those are your 7 diatomics. So if a problem says sodium reacts with, you would just write Na. If it said that rubidium is produced, you would just write Rb. But if it's one of these 7 elements, you write a 2 after it. Okay, so those are called diatomic elements. We'll get to the reason behind that later in the course. It has to do with the number of electrons the atoms have and how they bond, how the atoms will bond to each other using those electrons. But those 7 elements are diatomics. Okay, the halogens, hydrogen, nitrogen, and oxygen. Okay, so you want to make sure you have those down. So let me show you one more, because there's a lot involved in this problem, right? So let's take a look at this one, writing the chemical equation. Okay, let me share this one. Solid copper and aqueous iron 2 sulfate, Fe2SO4, I'm sorry, FeSO4 are produced by the reaction. So it's giving you the products first of aqueous copper 2 sulfate, CuSO4, and solid iron, right? The balanced chemical equation. Okay. So what I'm going to do is I'm going to write these down. So solid copper. Okay, well, that would just be copper is Cu, solid is an S. Okay, so solid S, liquid L, gas G. And then there's a fourth one, aqueous. We'll talk more about this in chapter 4, AQ. That one has 2 letters, AQ for aqueous. That just means dissolved in water. Okay. So solid copper, aqueous iron 2 sulfate. Okay. And then it actually gives you the formula, FeSO4. And it's it's aqueous, so we write AQ. Okay. Then it says are produced. These 2 are produced, so these are products. Because it says they're produced from or by the reaction of aqueous copper sulfate, copper 2 sulfate. Again, they give you the formula here. There's a way to figure out, a relatively simple way to figure out what the chemical formula is, but I'm not going to go over it because it doesn't, they give it to you here. So aqueous copper sulfate and solid iron. Okay, iron is Fe, not, be careful, it's not IR. IR is iridium. Fe is iron. Okay, it says solid, so I'll put an S there. Okay. And then it says are produced by the reaction of, meaning these are the reactants. Okay. So your first step is to write the equation. The arrow points toward the products, so CuS and FeSO4 aqueous. On the reactant side, we have aqueous copper 2 sulfate, so CuSO4, aqueous, plus solid iron, FeS. Okay, so there's our equation. This is actually pretty good. We've got the chemical equation written, but we don't have the balanced chemical equation written. We got to balance it now, okay? So what elements do we have? We have sulfur, we have copper, we have oxygen. So we got copper, sulfur, oxygen, and iron, right? 4 elements. How many coppers? I'm just going to start on the left and move my way to the right. How many coppers do we have here? 1. How many do we have over here? 1. So copper is balanced. Sulfur, 1 on the left, 1 on the right. Oxygen, 4 on the left, 4 on the right. Iron, 1 on the left, 1 on the right. Okay. Guess what? Every element is balanced here. It's the same for all 4 elements. 1, 1, 4, 1. 1, 1, 4. I'm sorry, 1, 1, 1, 4, right? It's the same. It's balanced. So this one, no numbers are going to be written as coefficients. Okay, so that one's kind of a gimme. It doesn't really help you get better balancing equations if you don't have to balance one. But we do want to point out that there are chemical reactions where, you know, everything is a 1. All the coefficients are 1s. And that's still a balanced equation. That does happen. Okay. All right, so let me, let's see. I'm going to do one more of this because that one was a pretty simple one, right? So let's come over here and let's see if we can find another one. Okay, here's one. So this one says chlorine gas and solid lithium are produced by the decomposition of solid lithium chloride. Ooh, okay. So let me go over that one. So solid lithium, that would be LiS, solid lithium. Chlorine gas, are formed. So that means these are the products. Formed, right? They're forms. That means they're products from the decomposition of lithium chloride. And here they give you the formula LiCl. Solid, it said, I'm sorry. Okay, so decomposition of. Decomposition means it's breaking up. So if lithium chloride breaks up, it decomposes. And it's a very common thing in chemistry for things to decompose. So lithium chloride is our reactant. So let me write this down. So LiCl, solid. It's going to decompose into, break up into LiS and Cl2 gas. Okay, we've got the equation. It's just not balanced. If you look at the chlorine, you can see there's 2 on the right, but only 1 on the left. So that's not a balanced equation. So how do we deal with that? How do we balance this equation? Lithium and chlorine, those 2 things. The lithium already looks balanced. So here's what I'm going to do. I'm going to show you a little algebraic step. See how there's 1 lithium on both sides? So that's already balanced. We've got 1 chlorine here, but we have 2 chlorines here. So here's one way to do it. This chlorine is all by itself here. So if we could make a coefficient, I'll put an X there. We could put a coefficient there so that it gives you a 1. The equation would be balanced, right? Because Cl2 is 2, but if I could somehow make it 1, then we would have 1 chlorine on both sides. We already have 1 lithium on both sides. So here's the trick I'm going to show you. It's not really a trick. It's just using common algebra. What we want is this X chlorine to be equal to 1. But we can't just change this to a 1. Can't do that, sorry. Can't change the subscript. The subscript is what it is based on the natural chemistry of things. So what we can do, though, is we can change the coefficient, because changing the coefficient is just like changing how much you're adding. It'd be like if I said, look, I'm going to make 2 cakes instead of 1. I'm going to use 2 cups of sugar instead of 1 cup. So the number of cups is essentially in the front. That's the coefficient. So you can change the number of cups of sugar or flour that you make in a cake, but it's still got to be flour. It's still got to be sugar, right? So we can't say, oh, well, instead of sugar, I'm going to use dirt. Or instead of flour, I'm going to use, iron filings, right? The reason we can't change Cl2 into Cl is Cl and Cl2, it's kind of interesting. They're just very different things. They're not the same things. We can't do that. But we can change the coefficient, how much is in there. So here's what I'm going to do. We've got a subscript here. So X times the subscript, we want that to be a 1 because we already have a 1 over here. So we want this to be 1. Okay, well, what would I do algebraically? If I said X times 2 is equal to 1, what would X be? Just divide both sides by 2. And you get a half. In other words, if this X were a half, mathematically it would work, right? You would have lithium chloride goes to lithium solid plus 1/2 Cl2. A half times 2 is 1. So it works. Now, here's the problem with that. There is a problem. And the problem is that in ALEKS, they will not accept fractions. They won't they won't even accept decimal numbers. So if you put 0.5 to be tricky, they would say no. It wants whole numbers. Now, that's not true in chemistry that we always do whole numbers, but ALEKS does. So how do we get rid of the half? How do we make it a whole number? You multiply everything by the smallest number you can to get rid of the fraction, right? So what times a half is a whole number? So if I take something and multiply by half, how do I get a whole number? Well, you can multiply by 2, and that would give you 1, right? So what I'm going to do is I'm going to multiply everything by 2. 2 LiCl goes to 2. I got to multiply everything. And then that gets rid of the half. If it's not a half, it's 1. Okay? Now it's still balanced, but now you've got whole numbers. 2 lithiums, 2 lithiums. 2 chlorines, 2 chlorines, all right? So in terms of just counting atoms, this is the same thing. If you're just counting atoms, which is what we do when we balance equations, we're just counting atoms. The 2Cl means 2 chlorines. Cl2 also means 2 chlorines, okay? But they're different things. 2Cl, what that means is 2 separate Cls. All right, let me write it this way just so you can kind of see the difference. What that means when you have a coefficient is you've got 2 different things. When it's a subscript, so instead of writing equals, let me put an arrow. Really what that means is you've got 2 of them, but they're attached to each other. So it's one thing, 1 Cl2. That's right, there's only 1 here. The inference is that there's a 1. That's the implication, is that's a 1. So there's 1 molecule of chlorine, okay? Here there's 2 atoms. 2 separate atoms turn into 1 molecule of chlorine. That's the idea there, okay? Now you've got your balanced equation, you've got the states of matter there, you've got the reactants and products set up, and you're kind of done with that one, okay? I'm going to do one more because I'm just about, I've got about 5 minutes or so here, but it's nice to do a few of these. Okay. So one more here. Let's try this. Aqueous sodium sulfite, Na2SO3, reacts with aqueous hydrochloric acid, HCl, to produce aqueous sodium chloride, which is, doesn't tell you what sodium chloride is, interestingly enough, and aqueous sulfurous acid, H2SO3. So they're not telling you what sodium chloride is. We'll figure it out. Okay. So aqueous sodium sulfite. Okay. That it tells you, Na2SO3. Reacts with aqueous hydrochloric acid. We'll talk more about hydrochloric acid in chapter 4. And they're going to react. So these are reactants. It says they're reacting. And they're going to produce aqueous sodium chloride. Aqueous, AQ. And aqueous sulfurous acid. And it tells you they're produced. It tells these are the ones that are produced, so they're products. So the arrow points towards the products, okay? Doesn't tell you sodium chloride. So see how I wrote sodium chloride here? Sodium is Na, chloride is Cl, so NaCl, okay? So reactants first, so Na2SO3. Don't forget the states of matter, plus HCl. Again, aqueous. Looks like everything is aqueous. We're going to get NaCl and H2SO3. Okay, so for this one, how many elements are there? You got sodium, sulfur, oxygen, hydrogen, and chlorine. There's actually 5 elements in here. Let's start on the left side. How many sodiums do we have? We have 2. How many on the right? Only 1. So that can be easily resolved by either making this a half times 2 is 1. But that's complicated. You know why in this case? That's going to make it a half of sulfur, and it's going to make 3 halves of oxygen. That's too complicated. So let's do this. Let's just put this one as a 2, right? So instead of doing half of Na2 to give us 1 sodium, let's do 2 NaCl to give us 2 sodiums, right? So now it's 2 on both sides. And then for that reason, we don't have to do the fractions and get rid of the fractions like sometimes we might have to do or might be inclined to do. So sodium is done. What about sulfur? Take a look at sulfur on both sides. How many sulfurs are on each side? Reactant side? Just 1, right? Na2SO3. There's just S. That's 1. On the product side, H2SO3. Oh, it's just S. It's just S, just 1 sulfur, right? The O3 means there's 3 oxygens. If we wanted to say SO3, if we wanted to say SO parentheses 3, then there'd be 3 sulfurs. But you'd have to put the parentheses around the sulfur and the oxygen together. Okay? So since there's no parentheses, that just refers to the oxygen. Sulfur's done. So sodium done, sulfur done. What about hydrogen? There's 1 hydrogen on the left, 2 on the right. Again, you could put a half in front of the H2SO3, but what is that going to do to the sulfur and oxygen? You'd have half a sulfur, 3 halves of oxygen. That doesn't seem to make things very easy. What if you just put a 2 here? Right? two hydrogens on both sides. So hydrogen's good. Let me write them down. 2, 1, 2. On both sides, right? On either side, it's the same. Now, what about chlorine? Chlorine, there's 2 on the left, right? The coefficient refers to the whole compound. So 2 hydrogens and 2 chlorines. But guess what? It does here too. We have 2 chlorines on both sides. What about oxygen? I didn't do oxygen. There's 3 on both sides. All 5 elements are done. You now have a balanced equation. Okay. 5, I think I did like 4 or 5 examples there just to go over them. Some of them are really easy. Well, obviously we saw one that you didn't even have to balance it. Some of them are really easy, just very simple steps. This is a pretty easy one here, right? I will point out in terms of these, sometimes it's useful to think of these as polyatomic ions. So SO3, we'll talk more about that later, is actually a polyatomic ion, SO3 2-. And notice they both sides have 1. So if you actually count the number of SO3s, it's 1 on both sides. So you can almost balance it together as a unit, or you can balance it together as a unit, 1 SO3 on both sides. That way you don't have to do sulfur and oxygen separately. Okay, so there's your balancing equations. Okay, so tomorrow what I'm going to do is I'm going to look at section 3.4 and maybe a little 3.5 combustion analysis. Okay, so I'll do a couple problems on those. And then typically I wouldn't do a lecture on Friday, but since I missed a couple days earlier this week, I'll do some problems on Friday on 3.6 and 3.7. And then that should wrap up this chapter. So at least by the weekend, you have a little bit on here. But again, keep in mind, these are just additional problems I'm doing this semester. Feel free to just kind of really go over all the details of the 6 lectures that I put up already from the previous semester. Okay, so take care and stay in touch.